I should say that it's a great honor for me to make a talk at the conference devoted to the anniversary of the prominent Rostov mathematician Nikolai Karapetyan's. Much work have been done by Nikolai Karapetyan, the theory of integral operators, in particular. And I want to begin my talk also with several examples of integral operators. As is well known, if H and H prime are two separable Hilbert spaces, an operator H between H and H prime is called Hankel operator if its matrix with respect to this basis Ek and Ej prime has entries that depends only on the sum of indices. And this definition hardly depends on the fact that H and H prime are separable Hilbert spaces. Hankel operators have several important realizations. In particular, the following integral, the next integral operator H between spaces Hardy spaces H2 on the circle T and its orthogonal complement H2 minus on the circle T looks as follows. Here, sigma is some fixed bounded measure on the complex plane supported in the disk, in the open disk D. And this operator was studied by the boundedness, the dependence of the boundedness of this operator on the properties of the measure sigma was studied by Vidum, Nikolai Kapitonich Nikolsky, and others. And the next operator A is a natural generalization of the previous Hankel operator H. Here Q is some complex parameter and absolute value of Q is less or equals to 1. And the next operator B is also the natural generalization of the previous Hankel operator H. And here the complex parameter Q has absolute value greater than 1. Both operators A and B are special examples of so-called mu-Hankel operators between separable Hilbert spaces. The theory of such operators was initiated in the next paper by me and my student Kuzminkova last year. And by definition, if H and H prime are two separable Hilbert spaces as above, the operator A between H and H prime is called mu-Hankel if entries of its matrix with respect to this basis has the following form. Here mu is some complex parameter, and of course, if mu equals to 1, we get the previous definition of the classical previous definition of Hankel operator between separable Hilbert spaces. And two problems remains unsolved in the previous paper mentioned above. The first problem is what is the structure of mu-Hankel operators, and the second one, how to define mu-Hankel operators in the non-separable case. And I'll begin with the second problem. I want to explain how to define mu-Hankel and in particular Hankel operators between non-separable Hilbert spaces. And in several important special cases, I explain the structure of such operators. In my opinion, the convenient approach to the non-separable case is as follows. We consider a compact abelian group G with the dual group X, and we fix a total group ordering in X. And with respect to this ordering, X plus is a so-called positive cone in X. This cone consists of such characters chi that greater or equal to the unit character 1. And the complement of X plus, denoted X minus, is a so-called negative cone. And Helson and Longenslager in this context defined the Hardy space H2 over the group G as the space of such functions in L2 of G whose Fourier transform is supported in the positive cone, and its orthogonal complement H2 minus of G consists of such functions in L2 whose Fourier support is supported in the negative cone. And the Hilbert dimension of H2 of G and H2 minus of G is the cardinality of X. And so if the group G is not metrizable, it is known that X is not separable, is not countable, I'm sorry. And so in this case, if G is not metrizable group, these Hilbert spaces H2 and H2 minus are non-separable spaces. And sorry, I can't list the next page. Full stop. Oh, thank you. So to define the mu-Hankel operator in this context, we consider as mu some homomorphism between the group X is the dual group of G, and the multiplicative group, semigroup C of complex numbers. Mu is some such homomorphism, so-called generalized character of the group X, and we choose some function A, a complex valued function on the positive cone, and then a mu-Hankel operator A sub mu A between spaces H2 of G and H2 minus on G is an operator with the following matrix whose entries looks as follows. It should be noted that X plus is the orthogonal basis of H2 of G, and X minus is the orthogonal basis in H2 minus of G. And so the scalar inner product A chi multiplied by xi bar is xi bar is the entry, the general form of the entry of the matrix of this operator A with respect to basis X plus and X minus of these Hilbert spaces H2 and H2 minus. So if we get G as G the circle group, this definition turns into the previous definition of mu-Hankel operators. And if the general character mu is identically unit, we get the definition of Hankel operators between H2 of G and H2 of G minus. In other words, A sub 1 A small is a Hankel operator on G, and the equivalent definition of the Hankel operator on G is as follows. We consider the orthogonal projection P plus from L2 of G on the H2 of G, the so-called Riesz projection, and define and we consider some function phi in L infinity on G, and we define the Hankel operator of the group G in the classical manner, H phi x on the function f as a is projection of the product phi multiplied by f. The theory of such operators, I mean Hankel operators of the group G, was developed in my paper in Algebra and Analysis, and several papers mentioned in the bibliography of this paper. And the first question, when the mu-Hankel operator over the group G is bounded. The following theorem 1 gives conditions for boundedness and the estimate of the norm of this operator. If mu is in L2 on the positive cone, then operator A mu A small extends from the linear span of x plus from the so-called subspace of analytic polynomials, of analytic type on the group X to a bounded, extends to a bounded operator between H2 and H2 minus if and only if the function A is also in L2 over the positive cone x plus. And the next estimate holds for the norm of this operator. And the important fact is that we can describe mu-Hankel operators as operators that satisfies the following operator equation 1. In this equation, A is a bounded operator between H2 and H2 minus. Mu is a general character of the group X. Chi is an arbitrary non-negative character of the group S, of the group X, sorry. S in the left hand side is the so-called unilateral shift in the group H, in the space H2, and S in the right hand side is the so-called bilateral shift, that X in the space L2 over the G. Left S X in the H2 and the right S X X in the L2. And this is the principal fact that allows us to give some descriptions of mu-Hankel operators in the non-separable case. First of all, I should say that the first positive element in the ordered group X should not exist, but often it does exist, and the first positive element I denote by chi sub 1. So we have the following theorem tree. This is a structure theorem, or the theorem for the mu-Hankel operator in the following case. Let Q denotes the value of the general character mu on the first positive element chi 1. And we assume that absolute value of Q in this theorem, we assume that absolute value of Q is less than 1, is strictly less than 1. So in this case, if the mu-Hankel operator is bounded, it has the following form too. Here, the nth element of the series in the right-hand side is the range 1 operator. The tensor product here denotes the range 1 operator between H2 of the group G and this operator acts to the one-dimensional subspace of H2 minus generated by the fixed function phi n, whose expansion in the Fourier series given in the next formula. Moreover, this operator is nuclear, and its norm is its operator norm has the following estimate. And it's important that this is the general form, since the converse of this statement is true. So formula 2 gives us the general form of the mu-Hankel operator in the case where, of course, exists the first positive element, and if the number Q, the absolute value of Q is strictly less than 1. The next theorem gives the similar description of the Mirotin operator if the absolute value of the parameter q is strictly greater than 1. In this case, the general form of Mirotin operator is given by the following formula 3, where functions Pn has the mentioned below expansion in the Fourier series over the powers of the first positive element chi sub 1. And of course, this is also the general form of a Mirotin operator in this case. In the case where the absolute value of q, of the value of mu at the first positive element, is strictly greater than 1. Surprisingly, the most difficult situation we get if the absolute value of the value of mu at the first positive element is equals to the 1. I think this is a difficult question, and I have only the following partial answer. If the group G is not equal to the circle group, the following theorem gives, of course, the partial answer, because we assume in this theorem that mu is a character of the group X. In other words, the absolute value of the values of mu equals to 1 for all characters chi in X plus, and it follows for characters chi in X. In this case, we can reduce the study of a mu-Hankel operator to the Hankel operator. In this case, if the modulus if the absolute value of mu is identically 1, corresponding mu-Hankel operator is a product of Hankel operator Hphi. Hp was defined above, and some unitary operator of very simple form. This is a shift in the space L2. Here is a shift in the space L2 with respect to some fixed element G of group capital G. And so the norm, for example, of the operator A equals to the norm of the Hankel operator Hphi, and it is given by the last formula. This distance between phi and the space H infinity of G, the distance with respect to the matrix in the L infinity. If G equals to T, theorem 2, 3, and 5 gives the full description of Hankel operators. But if G is not equal to T, as I said above, theorem 5 gives only the partial answer to this open problem. And now we can return to the example of operator A in the beginning of my talk. I want to apply theorems 2, 3, theorems 3, 4, and 5 to this operator A. So we choose the circle group as G, and in this case the dual group is the group set of integers. So the general form of the character of group G is given by the formula chi sub k of z is z to the power k. So these characters are numerated by the points k in the group z of integers, in the additive group z of integers. The positive cone x plus consists of such ik where ik is not negative, the negative cone x minus of such ik where ik is negative. And we assume that Q is a complex. I recall that in the example of the operator A in the beginning of the talk, Q was some complex parameter whose absolute value is greater than, is less than 1, is strictly less than 1. Sigma some finite in general complex measure on the open disk D in the complex plane. And we assume the following condition on the boundary behavior of the measure sigma. The next integral should be finite. And then I recall that operator A between H2 on the circle T and H2 minus on the T is given by the next formula. And to answer the question about the structure of this operator, we consider the sequence of moments gamma n of the measure sigma. And then I'm sorry, one of the previous theorems shows that this operator is mu-Hankel, where mu of xk is q to the power k. The function a of xk is gamma sub k minus 1. And one of the previous theorems shows that R is bounded, and its norm has the following estimate. And we can express this operator A as a series of one-dimensional operators by theorem 3, where phi n of z is the given functions. And maybe it is of interest that the adjoint operator that acts between h minus 1 and h2 over the circle group has the following just surprisingly complicated form. This is a well-known approach how to transfer the operator between h2 and h minus 1 to the operator that acts from h2 to h2. We consider the so-called flip operator J. This operator J is a unitary operator between h2 and h2 minus. And then our operator A turns to the operator GA of the following form. And this operator acts from h2 to h2, as was mentioned above. And since this operator acts in the Hilbert space into itself, we can consider the trace. This operator is nuclear, and we can consider the trace of this operator. The trace of GA has the following form. And we can consider also the case where the absolute value of Q equals to the 1. In general, the definition of the operator A is consistent if the absolute value of Q or strictly less than 1 or the absolute value of Q equals to 1. The case where the absolute value of Q greater than 1 make no sense in this situation. And the previous formula gives us the structure of this operator if the modulus of Q is strictly less than 1, and if the modulus of Q is equals to the 1, this operator also is mu-Hankel, as theorem 5 shows. And due to the theorems of Widom, Nikolsky, and others, we can give the answer about the boundedness of this operator between h2 and h2 minus in terms of the measure sigma. If sigma is positive measure, then this operator is bounded if and only if the sequence of moments gamma n is capital O of 1 over n. This is in fact theorem of Witten. And if sigma be a general complex measure, then we have the sufficient condition. If sigma is a Carlson measure on the disk, then the operator A is bounded as operator between H2 and H2 minus 1. Here I list several papers with connection with the previous talk. The first paper about the Mill-Hankel operators in separable case, the second paper about the Hankel operators in the general case of the compact abelian group G, and the last paper is devoted to the theme of my talk, and this paper exists only as preprint and archive. Thank you for your attention.
Thank you very much.